remember we were talking about the method of least squares, right? Least squares. Right. And so just to quickly recall the problem, right? You have ax equals b, right? You're trying to want to solve ax equals b, but there's no solution, right? A is an m by n matrix, and m is bigger than n, and there's in general there's no solution. So instead we change it to find x hat so that the norm of ax hat minus b is minimal. Right? We change it to this problem, which maybe is solvable. Okay. We change that to we rephrase that as find p in the range of x, in the range of a, so that p minus b is minimal. Right? That's the same thing, right? Let's try to find the p who is in the range of a so that p minus b is minimal, right? But then this becomes something easier, or at least something more easily visualized. Range of A is a subspace, right? In the subspace, range of A, where this thing is minimal. So the game comes down to this, right? You have some B that's not in the range of A, right? You have some B that's not in the range of A, and you're trying to find the P that is in the range of A that's closest to that, right? You want to find the P in the range of A that's closest to that. And we have this theorem that says sort of what you think is true is true, that the P that's in here is the one that you get when you project this thing perpendicularly down, right? That would be your guess, right? What guy in this subspace is closest to B? Well, it'll be the perpendicular projection of B down onto the space, right? So we have this theorem that says, P let express B as B in S and plus B in S perp, right? Where in this case S is the range of A. Then the closest vector in S to B is B sub S. Right? And the reason we can do this is because Rn can be expressed as S direct sum S perp. Right? This is the key. Right? This is the key fact. That we can decompose our space into the subspace and the direct sum of the orthogonal complement to the subspace. Okay. And so that answers our question, right? What P will work? It will be the right. So the answer to our question, the answer to our problem is, well, actually, what x is such that b minus ax is in Ra perp, right? Because that's what we want. We would like to find the vector so that b minus that vector is in the orthogonal complement, right? Right? We want we want, this is ax, we want the ax so that b minus ax is perpendicular to the range of A. Right? This is what we need. We need the x so that b subtracted, if b minus ax is a vector that is perpendicular to the range of A. Okay. Right. At this point, we invoke the fundamental subspaces theorem by the fundamental subspaces theorem. That's saying b minus this must lie in the null space of A transpose. Right? We can translate that problem into this problem. The problem is what x is such that this lies in the null space of that. In other words, A transpose of b minus ax is 0. I.e., you want x so that A transpose ax equals A to B. Okay. And this is the sort of the ultimate reduction of our problem to something called the normal equations. So our problem of solving for the solution that is that minimizes our error boils down to solving this problem. Right? There is no answer. There is no answer to our problem. However, we can find something. We can find an answer that has a least error, a least squares error. What's called a least squares error. Okay, and we do it by solving this. Okay. Everyone see how that happens? Right. This is the story, right? That we're looking for this guy x such that this is minimal. Well, that's the same thing as looking for the guy p in range of A such that this is minimal. Well, we have from theory the fact that that's going to happen whenever p is whenever p is the perpendicular projection of b onto the space, right? When p is this thing, right? In other words, we want b minus that thing to be perpendicular to the space. In other words, by the fundamental subspaces theorem, that thing must lie in the null space of A transpose, which is, say, this. Any questions about any step? So we just take in thing and we translate it. Okay. And it's not all simply translation. We've also used various used two theorems, right? Fundamental subspaces theorem and this theorem about what vector is closest. Okay. So, Haley, yes, do you have a question? No. Okay. So, remark: if we're lucky, A to A is invertible. Might be invertible. In which case, x is unique. Right? X will then be ATA inverse AT. Okay. And in that case, this map, ATA inverse, ATA inverse, ATB, sorry. AT inverse AT is the projection, is the orthogonal projection map of Rn onto the range of A. So, if that happens, then a couple of nice consequences occur, right? You can solve for x hat uniquely, and further you get as a bonus you get this thing is the orthogonal projection map onto a range of A. That's kind of cool. I know it's useful, but it's sort of cool. So so x hat is unique. It may not be unique, right? It may not be unique. You could have multiple x's that work here. Okay, let's do an example. Okay, so this is an example. I'm afraid it's from your text. It is find the quadratic function that has the best least squares fit to the data 0, 3, 1, 2, 2, 4, 3, 4. In other words, we want the quadratic function p of x equals c naught plus c1x plus c2x squared, such that zero, 0, right, such that C naught is 3, right? C naught plus C1 plus C2 is 2, right? 1, 2, 4, right? C naught plus 2C1 plus 4C2 equals 4, and right, C naught plus 3C1 plus 9C2 equals 4. Right? Right.
Yeah, I don't get
the matrix?
Yeah.
Yeah. So the matrix is actually a translation of this request here, right? We want a quadratic function so that p of 0 equals 3. So that p of 1, we want a quadratic function so that p at time 1 is 2, p at time 2 is 4, p at time 3 is 9. Right? Right. We want a quadratic function p such that these 4 points are hit. Right?
Where's the 9 coming from?
Oh, I'm sorry. 4. Yeah. Right. P at time 3 is 4. Right.
Oh.
At time 0, right? When x is 0, 3, at 1 it's 2, at 2 it's 4, and at 3 it's also 4. Okay, so there are 4 points, and somebody says, give me a quadratic function that passes through these 4 points. Okay, it's impossible, right? But we can find a quadratic function that does pretty well. Okay, pretty well in the least square sense. Actually, the best in the least square sense.
I just don't get how you got the matrix.
Yeah, so you say, okay, we want this thing to happen. In other words, right, p at 0, that's to say c naught plus 0 plus 0 is 3. P at time 1, c naught plus c1 is 2, right? P at 2, that's to say c naught plus 2c1 plus 4c2 is 4. And P of 3, 3c1 plus 9c2 equals 4. Right? So I'm going to take this information and matrix it up. Right? Here it is right here. Right? I've written what do I want? I want c naught plus 0c1 plus 0c2 to be 3. I want c naught plus c1, oh, this should be 0. No, it should be, I'm sorry, this should be c2. Right? Right? Because p at time 1 is c naught plus c1 plus c2. So I want c naught plus c1 plus c2 to be 2. I want c naught plus 2c1 plus 4c2 to be 4. I want c naught plus 3c1 plus 9c2 to be 4. Okay, so I'm taking this information and I've just turned it into a matrix. Okay. So, but even so, even though I've turned it into a matrix, that doesn't help me because it's unsolvable. I've got four equations and 3 unknowns. Okay. It's unsolvable. There's no solution. There's no solution, but that's okay. We don't care, right? All we want is the best solution, the best possible solution. Okay, so we translate this, right? We say the normal equation, right? This is our A. This is what we're looking for, and this is our B. Right? Right? So we want we take A transpose A x equals AT B. Okay. So you take your matrix, you transpose it. Right? 1 0 0 1 1 1 1 2 4 1 3 1 3 9. Multiply it by the A. 1 0 0 1 1 1 1 2 3 1 4 9. C naught C1 C2 equals A transpose. That's your system, and then it turns into, you calculate it, it turns into this one: 4 6 14 6 14 36 14 36 98. C naught C1 C2 equals 13 22 54. Okay, which actually is solvable. In fact, this is invertible. So you invert it, and you end up with C naught C1 C2 turning out to be 2 3/4, negative quarter, and a quarter. Okay. And so that tells you those are the coefficients, right? So P of x being 2 3/4 minus a quarter x plus a quarter x squared is the best least squares fit to this data. It gives you the best guess you can get. It is it's basically a souped up version of this that is used by programs to reconstruct images, say. Like if you have have I shown you this sort of thing? Did I show you anything like this? You have a picture, and then the picture is damaged, and then the program makes a guess as to what underlies the damage. Did I show you this? Maybe I'll bring it.
Is this Stanford?
But, so that was the reading the brain sort of thing, like reading the mind. Was that what I showed you on the first?
Yeah, I turned it
Yeah,
on.
you showed us that
Yeah.
one.
Okay, so that's something else. It's related, but it's something else. Yeah. So there's another really amazing example of this. You have a picture and somebody has typed letters all over it, right? And then you don't know what underlies those letters, but you're able to make you make some sort of guess based on a library of information, and it allows you to reconstruct what underlies it. So, I think there are programs now where you can erase people out of your photographs, right? You can say, I'm going to erase this guy, and I'd like to replace him with this fitting scenery, right? And the program will basically guess as to what the scenery should have been underneath that guy, and then he's gone. Right? It's just like if they were like part of a bookcase, then the program will, I think, try to reconstruct the bookcase that was blocked, the part that was blocked off by that person. Yeah, amazing what can be done. Okay. And and that this is not exactly a lie. I mean, this is not exactly true, but it's not completely wrong to say that that's sort of a super version of the method of least squares. Yeah. Okay. So everybody see how to do it, right? We've got this problem, right? So part of the problem was taking this problem and turning it into a matrix problem. Okay. Once you've overcome that, then it says, okay, now we've got this different problem. We have an overdetermined system. Well, now we have this method of solving not solving, but getting the best answer to the overdetermined system, right? And if you read in your textbook, this was pioneered by Gauss, right, the greatest of all mathematicians, in using it to predict the location of Neptune or something like that. Right? They got certain estimates. They saw Neptune at one place, and they saw Neptune at another place, and they were for some reason trying to make some guesses as to where Neptune would be on another a subsequent date, and the great astronomers of the day made all these guesses, but none of them Gauss's guess beat everybody's guess completely, and it's because he used the method of least squares. Okay, one last comment about this. So we did comment that it would be a good thing. So it's nice if A transpose A is invertible. Right? So when is A transpose A invertible? We'll give a theorem that gives one condition. So A is an m by n matrix, right? And remember, m was bigger than n. If the rank of A is n, then A transpose A is invertible. Proof is we'll show that the null space of A transpose A is 0. that will be enough to show that A transpose A is invertible. Because you have a square matrix and its null space is 0. So maybe I'll let you try. See if you can try to say anything. Yeah, just spend the next 2 minutes trying to say anything at all you can say in this direction. You don't have to come up with a full idea, but just come up with one observation, say, that you can say about, right? Let's let X be in the null space. Then say one thing. And hopefully that one thing will lead to us saying X is 0. Right? That's our goal. Something on your forehead. Yeah, something on your forehead. Styrofoam is a piece of stuff. Yeah, you got it.
It's getting.
Sorry, I was trying to say it in a more calm way. Yeah, you got it. Yeah, generally I try to say everything in as calm a way as possible. Trying to make it even calmer.
How do your kids feel? Like if they're in trouble, are you always very calm with them?
Go to your room.
That's worse.
That's worse.
No. Actually, with my kids, I often lose my calm.
Okay. Kids do that to you.
Okay. Okay. What can you say? Right. X is in the null space of A transpose A. Right? So what? So what? Well, first off, we can say, what does that mean, right? Being in the null space means what?
AX equals 0.
Not that AX equals 0, but that this
ATA,
X equals 0, right? That ATA X equals 0. Okay. Can anyone say anything from here? This is just like any sort of deduction or observation. Yeah, so I mean, a lot of this is just making, just observation after observation, and hoping that one of those observations will lead us to the place we're trying to get.
Are we working with like the associativity of the null space?
You can't say that. Oh, yeah. So certainly you could say that AX equals 0. Yes, that's true. So that is to say, AX is in the null space of AT. Great. That's great. Can anyone say anything from there? AX is in the null space of AT. Mia?
Does that mean it's also in the null space of the range of A?
It's in the orthogonal complement of the range of A. Yeah. So this is in, right, by the fundamental subspaces theorem, this is that, right? So AX is in the orthogonal complement of the range of A. Great. Yeah, Mia?
For AX to exist in both, does that have to equal 0?
Yes, yes. So AX in both what?
The null space of A transpose and both those things.
No, these two things are the same thing. These two things are the same thing, so it doesn't matter.
Oh, if it exists in the null space of A transpose and the null space of A.
And the null space of A, it's not in the null space of A. It's in the null space of A transpose. It's in the perp of the range of A. So what would make it 0? It lies in the perp of the range of A. It would also lay in the range of A, then that would make it 0, right? If it lay in the range of A, then that would make AX equal to 0. I'm sorry, AX equal to 0. Right? Does AX lie in the range of A? Does AX lie in the range of A? Yes, by definition, right? AX is in the range of A. Right? So AX is 0, right? Because AX lies in range of A and the range of A perp. Okay, does that make X equal to 0? Does that make X equal to 0? Why? It's a right. Great. Right. The rank of A is net n, so that gives you that the nullity of A is 0. Right? That is to say the dimension of the null space is 0, so if you're in the null space, you must be 0. Right? So X must be the 0 vector. That's 0. Let me write this up a little bit more cleanly. But first, go ahead and ask me a question.
Actually, no.
Okay, so let me write this up more cleanly. Okay, so right, because this is just sort of a sketch, but it doesn't really. We haven't. This would. You haven't really justified things if you write something like this, or I haven't justified things. Right? So say X lies in A transpose A. Oops, in the null space of A transpose A. Null space of transpose A, i.e. A transpose AX equals the 0 vector. But that gives us that A transpose AX is the 0 vector, which gives us that AX lies in the null space of A2. By the fundamental subspaces theorem, NAT is equal to RA perp, right? So AX lies in RA perp, but AX lies in range of A, So AX lies in RA perp intersect RA, that is to say 0. And you, maybe to be proper, you should cite some theorem that says that the intersection of S, that's a pretty obvious fact, so maybe you don't need that. Okay. That tells us that X lies in the null space of A, right? But the rank of A is n, so the rank theorem implies that the nullity of A is 0, i.e. the null space of A is the 0 vector, so X is the 0 vector. Right? So thus, the null space of ATA is the 0 vector, and so ATA is invertible. Yeah, Elena.
Is there a reason that you can't, from there, just say because the rank is n, the nullity is 0, so A is invertible, which means its transpose is also, and then the product of two invertible matrices?
A is an m by n matrix.
Okay.
Yeah, yeah. A is an m by n matrix where m is bigger than n. So yeah, so it, if it were an n by n, then yes, that would be it. Yeah, that's why. Yeah, why. So, just as a matter of how to write mathematics, right? This is I think a pretty good example. I would say, you want to show that ATA is invertible. It suffices to show that the null space of ATA is 0. So say that you have something in the null space of ATA, blah 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 blah. It is 0. The end. So this is a pretty good example of proper argument. Like one has to, these things are when you use IE, it's basically saying that I'm not saying anything new, and I'm saying exactly the same thing as before, exactly the same thing as before, exactly the same thing as before. And now I'm making a conclusion. I have to say why I'm making that conclusion. Right? This happens for some reason. Question? Yeah, Teresa.
How liberally can you use those arrows? Like, do they have to? If
So-
you're restating something, you can't use the arrows.
You could. So if instead of using the IE, I could use a double arrow.
Okay.
Right? Meaning that this statement is exactly the same thing as this statement. Is exactly the same as this statement. Exactly the same as this. Yeah. So those are sort of interchangeable. I tend to use the arrows for more significant equivalences, and I use IE for things that are pretty trivially equivalent to each other. But the double arrows just means is equivalent to, right? And then the forward arrow implies that. It's a then, basically. Okay. Other questions? Okay, so that is it for 5.3. Let's go on. Don't want to waste time. The more we do, the more knowledge you get. It says 5.4, scalar products and norms for abstract vector spaces. Okay, so what we're going to see is that what we're going to do is put a dot product on abstract vector spaces. Okay. We have some vector space, and it may be that we're able to put something like the dot product on these spaces. And it turns out that if we can put this thing that is like the dot product, then certain properties that held true in Euclidean space will still hold true in these abstract settings. So it'll be sort of like putting a geometry on the space which didn't seem to have any geometry before. Okay. So here is the definition of the abstract dot product. Okay, and it's what's called an inner product. Okay. So you have V, a vector space, V, a vector space, and you have this thing bracket bracket going from V cross V to R. So it's let this be a binary operation on V. Okay. By that I mean it takes in two vectors, right? It takes in something, some vector here and some vector. It takes in two vectors in V and then returns a number, right? Taking in two vectors and returning a number, a scalar in R. Right? And to be honest, we could make this into C, but for now we're going to make it into R. Okay. Okay. So you have this binary operation, and if it satisfies the following three properties, then we call it an inner product. Okay. So here are the things that we want to happen. We want V against itself to always be a non-negative number. And we also want V against V to be 0 if and only if V is the 0 vector. Okay. Second, we would like this product to be commutative. We'd like this product to be commutative. And third, we'd like this product to be linear in the sense that alpha x plus beta y comma z should equal to alpha x comma z plus beta y comma z. Right, for all x, y, z in V and all alpha beta in R. Okay. So if those things happen, then we say this brackets, is an inner product on V, and call V with this brackets operation an inner product space. Mia.
So, if you have an alpha in front of the bracket, you only multiply it by the first one, to the first one.
Well, what you're talking about this last property, right? Just think of the last property. If I had like alpha u plus beta, if I had like 3u plus 5v, and I took the dot product of that against some w, right? What's that going to equal? That's going to be 3u dot w plus 5v dot w, right?
Okay.
And so that's what you want to happen, right?
Okay.
I'd like this against that to be alpha of x against v plus beta of y against z. let me just quickly put up one example. I'll put up a whole bunch of examples next time, but here's the one example I want to show you. B is the continuous functions on AB. So continuous functions on the interval AB. Right? And we define the inner product of two functions by taking the integral of one against the other. Okay. This, the above, is an inner product. Okay. This is something like a dot product. To check that, we have to check all the properties. Let's look at the second and third ones first. Suppose we rearrange the order. Do we get the same value? Sure. Suppose we have alpha x plus beta g and integrate that against h. Am I going to get alpha of the integral f against h plus beta times the integral g against h? Certainly, right? So those two properties are true. What about the first property? Is it true that if I integrate a function against itself, I always get a non-negative number? Is that true? If I integrate a function against itself, I always get a positive non-negative number?
Area can be negative.
So if I take f against f, what do I get? I'm going to get the integral of f against f, right, from a to b. What do I know? What do you know about your integrand? Your integrand is it's a square, right? It's a positive number or a non-negative number. So you're integrating something non-negative, and so you're going to get something non-negative, right? Right. So the first part of property 1 is true. What about the second? Is it true that if I get 0 here, then the function must have been 0 everywhere? If I get 0, what does that mean? Right? If I get 0, then that's to say that the integral of f squared x from a to b is 0, right? Right? Does that tell me that the function, does that imply that f must be 0 everywhere? You can sort of say the opposite. Suppose f is not 0 everywhere. Does that will that cause my integral here to be not 0, to be bigger than 0? Yes.
Doesn't f have to be 0 because it's always positive, or it's 0? Like it can't go like below. Never mind.
It's true that, so the opposite is true, that if I'm integrating something positive, then I'm going to get, if I'm integrating something that's bigger than or equal to 0, I'm going to get something that's bigger than or equal to 0. Okay? But what about the opposite? Is it true that if my integral is 0, then my function must be 0 everywhere? It's actually a little bit subtle, because if we weren't dealing with continuous functions, then you could have a function like this, say, right? A, B, right? The function at some points takes certain values, but the integral is still 0, right? Okay, so it's actually because of it is true, one has to use, it's because of the continuity of the function that causes this to happen. So this is true, yes, because of continuity. Okay, so this thing actually does turn out to be an inner product. So now we have something like a dot product on functions in the space of functions. Okay, and we'll talk more about this next time.